Okay, so welcome to lecture 5. And in this lecture, we're going to start to deviate away from the GCSE syllabus and move now onto the A-level syllabus. And what we're going to be looking at is differentiation. So differentiation is a part of calculus. So for the next couple of weeks, we're going to be discussing calculus. But first of all, we'll start off with differentiation. And in short, as I'll come to describe, differentiation is just a very fancy way of doing division. So let's maybe explain where it comes from. So I'll start with drawing a line here and something which intersects it like this. So we have a tangent to the normal, and then we're going to draw a curve that crosses the line here. So what we're aiming to do with differentiation is we're looking for a contact point, so a point in which a line crosses at a very, very small point. So if we have a curve, there's only going to be one really, really small point in which this point will cross. We'll call that A. And we're going to have a look at our next point, another one of these that we choose along the line, B. And we're going to look how we can connect them and begin to describe the curve. And what the aim is if we can think of a straight line, what we might have done at GCSE that looks something a little bit like this, and we've described that as dy over dx, which is our gradient. What we're going to do on our curve is we're going to describe the very, very, very small changes which we're describing locally what the gradient is. So we're going to make we're going to make an expression from an equation, and what that's going to do is make a local expression for how the curve changes. So in essence, we're going to describe how a curve is changing. We're going to be finding its differential, which is how the rate of change of the curve. So we can think of this maybe as a change of a change. So perhaps in the real world, you can think of this if you're walking along a path. The path is curved, and as you walk along the path, your direction is constantly changing. So locally, you're changing. And each point, each time you change a little bit more. And if we had that equation, we could make an expression to describe it. So let's describe this with a few numbers then. So for example, if I have a plot that looks a little bit like this, I'm going to put our y-axis on and we'll put our x-axis on, quite customary. And then what I'm going to say is this is going to be a function of x squared. Okay, we'll just plot x squared and we'll draw this nice bucket here, which we described by x squared. So what we need to think of is if we take one of these contact points at this point here, A, and then we think of what our description of what we have here is, we can actually describe the location of A by saying, well, if this is at point X, then it has to be, its Y location has to be X squared, and that's what this function showed us. Likewise, now, if we were at point B, we've moved a little bit, we've moved a delta X, so we would say our first coordinate would have to be B x plus delta x. So this little symbol here means change, a very small change typically in mathematics. And we use it quite a lot, especially with differentiation, and we'll talk a little bit about that later. So if we have x plus delta x, which is our small change here, and then we can say, well, okay, so what would that be in our y location? Well, we know our function. So if this is our function, that goes back into x, which would mean that this would be x plus delta x squared. So now we actually have two expressions. We can begin to describe what A is and what B is and how they relate to each other. And if we can think of this delta x as being so small, mathematicians like to use this, so small that we don't actually notice it, then what we can begin to do is describe our local curve. So again, if we go back to our y equals mx plus c, and we've described over here delta y by delta x, well, now we actually have B and we have A. So we can begin to describe what our locations are. So maybe we put our B here, our change in Y, over our change in X. So that would be, we'd have X plus delta X, which is our change in Y. But then it's changing in Y because we have to minus our X squared away from it here, like this, minus X squared. And over A, where we have our change in X, which would be x plus delta x minus x. So x plus delta x minus x. Okay, so that's made us some expression here, which, sorry, that should be squared. So we have something quite neat. So what we can actually begin to do here is say, right, so what we described here is that b, we had, in the y, we had x plus delta x squared, which is here, tick. We had to find out how it had changed in the y, so that changed from y, so we just minus the 2. And likewise, we had the change the x here, which was x plus delta x here, and we had to find out how that's changed in y, so we have x. Remember, we're doing this because when you find out your gradient on y equals mx plus c, you're always looking at the change in y over the change in x, and that's what we need to do here. So if we were to just neaten this up a little bit, what we'd actually find is we could say, well, we have very similar equations here. We can actually begin to neaten it up. So that would cancel with this. We could multiply this out, and then we could say that the x squared, so that would be x squared plus x, or 2 delta x plus delta x squared minus x squared, and that would be all over our delta x. We can see that we can cancel those two out, and then we have deltas in here, so that would be 2x, and we get rid of that term. So we've actually got an expression here which looks like 2x plus delta x. So that would be our expression of how these 2 points have changed. But in mathematics, often, as I mentioned, this delta x is so small, we say it limits. So delta x would limit towards 0. So it becomes so small, the limit would be 2x. So that would mean our answer would just be 2x. But what we say here is what we've shown is our change in y over our change in x is equal to 2x. And that would be our expression. Okay, so that's work for x squared, and as I've shown before in previous lectures, we've had issues where we change some numbers and things change. So let's try something a little bit more realistic. What happens if we had the function of f of x equals x cubed plus 5? So if we start by drawing our axes here again, and we're going to plot these, so we know it crosses at 5, so we've got to have something here. We'll put y, we'll put an x, and we know an x cube would look a little bit like something like this, so that's crossing at 5, so we're going to have something that looks a little bit like that for a cubic term. So likewise, we can pick any point on the plot, it doesn't matter where we are, so maybe we choose something convenient like this here, and we say our a value. Okay, so we've got our function, and we're starting at our first point, x we'll call it. So we stick this in, and we will get our first value, which would be, if x is x, that means that this will be x cubed plus 5. Okay, and if we choose our b point again, if we choose our delta x there, and we're going to add a delta x to it, and we want to actually find out what that delta y would be, we could figure that out. So we could say that the b would be x plus delta x, and our y value would have to be x plus delta x cubed plus 5. Okay, so that's not that difficult. So all we've done is we've put this value into here, and we've got our x value, which we've put into our function where our x is, and we see that this was a function of x, and to x cubed, and our 5 goes on the end. So as previous, we can now begin to build our equation. So I'm going to use some different types of brackets here so we don't get confused. So this would actually then write down as x plus delta x cubed plus 5 minus x cubed plus 5 all over x plus delta x minus x. So again, we can begin to tidy this up. These x's would cancel, and if we multiplied all this out, I'll let you do the proof yourself, the answer we would get would be 3x squared plus 3x delta x plus delta x squared. Okay, but what I've shown you previously is because these delta x's are so small, we could actually say from the limit of these that these would go to 0. So effectively, we could say that delta x equals 0. Therefore, this value would disappear, this value would disappear, and we would actually find the differential, or our change in y over our change in x, would equal 3x squared. And that would be our description of how the gradient changes for our function, which is f of x, x cubed plus 5. And that would be our first differential. Okay, so maybe we've spotted something here. The same relationship goes on. So previously we had x squared, and that goes to 2x. And now we've had x cubed plus 5, and that's gone to 3x squared. So do we have this relationship? Well, yes, we do. We actually have an equation, and the equation states that d by dx axn equals anxn minus 1. So that's what we're doing. But in easy terms, there's a song that helps you remember this. So here we go. If we have x squared, we can say to differentiate, you've got to be sly. Bring the power down and multiply. Be really cool, get the job done, reduce the power by a factor of 1. So there we would have as 2x. Likewise, let's take our next one. So we have x cubed plus 5. So to differentiate, we're going to have two terms in here, but this hasn't got an x. So this has to disappear because there's no x. So we can say to differentiate, you've got to be sly, bring the power down and multiply, be really cool, get the job done, reduce the power by a factor of 1. And all of a sudden, we have our second answer, which is 3x squared. So what we've got here is a way, you can follow this equation if you want to, you can follow however you want to do it, a way of getting to that final answer. So I have made a little bit about notation, and it described a little bit more in the book. So depending on what books you'll read and depending how it's described, you might see something which is described by d by dx opposed to delta by delta x, or delta y, or dy, or delta y, depending what we're looking at as the function. And what this actually means is mathematicians like to switch quite a lot between it, but the general rule of thumb is if you're describing something real, we tend to use dy by dx. And if we're describing something which is very, 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 very small, we'd use delta y by delta x. In reality, it doesn't really matter. We understand what you mean, and mathematicians like to trick us out often with this. But if you want to use one, you want to use the other, that's fine. But if you're doing the first principle stuff, it is better to use this. But if we're looking at some of the real problems, maybe in the mechanics section, I'll be using dy by dx. But I might swap myself because I might get confused. It's quite easy to do. Okay, so let's apply this to some real examples and just show you a little bit more about differentiation. So first of all, an exam style question, one of the quick questions might be, differentiate with respect to x, y equals 3x squared minus the square root of x plus 1 over x minus 2. Okay, so before we do this, let's just make this a little bit tidier and put these maybe into these index form. So we'd say that y equals 3x squared minus x to the power of a half is the same as a square root plus x to the power of negative 1 minus 2. Okay, so we've tidied this up a little bit. So what we can say now is we can differentiate this. So we can say dy by dx equals, well, the first one we can say is, well, we bring the power down, multiply, be really cool, get the job done, reduce the power by a factor of 1. So that would be 6x to the 1. So that doesn't really matter. We can get rid of that. We can say that would be minus x to the minus a half. So that would be minus x. So we multiply a half x minus, well, 1 minus a half minus that is equal to negative 3 over 2. Plus x to the minus 1, which would be x to the minus 2. And what we can then begin to do is just tidy this up a little bit. So we'd say that dy by dx equals 6x minus 1 divided by 2x to the 3 over 2, because remember our negative swaps it, plus 1 over x squared. And that would be our answer. So this expression would describe what the gradient or the local gradient of that curve is. So you might think this is a bit kind of useless and you don't understand it. We'll go on to do one more example here. We'll do two more examples, and then I'm going to show you something called stationary values, and then we're going to solve some real world problems and actually show you how calculus is used. So again, maybe another example, as in the book, might show us that where an exam style question might be x minus 3, x squared plus 7x minus 1. So what we need to do is we need to multiply all this out. So we spend our time, we multiply it, we'd have an x cubed term, we'd have x cubed, we'd have 7x squared, we'd have minus 1, then we have a minus 3, 3x squared plus 7, so it's 21 minus 3 plus 3. So if we tidy that all up, we'd get something like x cubed plus 4x squared minus 22x plus 3. So now we can say that dy or dy by dx equals 3x, so multiply by 3, plus 8x minus 22, and our 3 doesn't have anything because we have nothing to bring down, which would equal 0. So this then would be the answer to our question. So again, the descriptor of the descriptor of the curve describing that would be this. And finally, we'll just do one more example, maybe a little bit more difficult, and then we'll go on to describing some stationary values. So C. So a trickier exam style question might be t equals 6z squared plus z minus 4 all over 2z. Okay, so what we want to do here is we want to break this down a little bit. So we can say that t equals 6z squared divided by 2z plus z divided by 2z minus 4 divided by 2z. So we can just tidy this up a little bit. So this z here would cancel with this, and our 6 would cancel with our 2 to make a 3. So this would be 3z. Our z's cancel here, so this would be plus a half. And finally, our minus 4 over z, we can have to keep it like this, 4 over 2z. Okay, so now we'll write it in index form, or we can cancel our 2's here. So we can write it in index form, where that would be 3z plus a half minus 2z to the minus 1. Oops, badly written. 2z to the power of minus 1. So we can say our delta z by our delta t, because remember this isn't a y, we have a z here, and our change in z over our change in t is therefore equal. So we have no power, we bring that down, so that would be 3. We have no x here, so that would be 0, plus our minus 1. Minus 1 is multiplied by here, so that would be a negative times by 2. So we'd have positive 2, so it'd be positive 2z to the minus 2, which we could describe as 3 plus 2 over z squared. Over z squared. Okay, so that would be our answer to our problem. And again, this would describe our local curve, or the local position of the curve at any point. Okay, so what we're going to do now is we'll move on to our next point, which is stationary values. I'll leave this video here, and we're going to describe stationary values and how curves change.